This is section 2.2, limits and infinity. And we begin with this comment that there are various possibilities under which the limit as x approaches a of f of x does not exist. For example, if one-sided limits are different at x equals a, that means the left-hand side is not equal to the right-hand side. Then we say the limit does not exist. Another situation where a limit may fail to exist involves functions whose values become very large as x approaches a. And the special symbol for infinity is used to describe this type of behavior. So when the limit as x approaches a of f of x is equal to infinity, we say that the limit does not exist. We answer in terms of infinity still, because there will be times when that answer of infinity becomes beneficial at a later time in our discussion of calculus. So we have this example to consider. It says to illustrate the case, consider the function f of x equals 1 over x minus 1. So they're giving us a rational function. This is discontinuous at x equals 1, which means that we have a vertical asymptote at x equals 1. We see that if we look at this graph where x is equal to 1, this vertical asymptote tells us that the limit from the left-hand side is going to negative infinity, and the limit from the right-hand side is going to positive infinity. So the limit does not exist. It's going to do two different forms of infinity. However, it's possible that we have a graph that has a vertical asymptote at x equals 1, where the left-hand side of the graph and the right-hand side of the graph both go up to positive infinity. G of x equals 1 over x minus 1 in parentheses squared would do this. So now the left-hand side and the right-hand side both equal positive infinity. So the limit of g of x as x approaches 1 is equal to infinity. But infinity is not a limit. When we talk about limits, that means we have an upper bound or a lower bound, a value that we cannot pass. And infinity is not a bound. We keep going on. So even though we can say the limit is infinity, there is no limit. The values for y will increase indefinitely as we get closer and closer to 1. At times we want to use infinity as the answer, and at times we want to state that the limit does not exist. So let's look at this. Infinite limits and vertical asymptotes, they give us this definition. The vertical line, x equals a, is a vertical asymptote for the graph of y equals f of x if f of x goes to infinity or negative infinity as x approaches a from the right or left-hand side. That is to say, f of x either increases or decreases without bound. So we should be familiar with saying increases without bound or decreases without bound as x approaches a from the right side or the left side of a. Another note, if any one of the four possibilities is satisfied, this makes x equal to a vertical asymptote. Most of the time the limit will be infinite, whether it's positive or negative infinity, on both sides, but it does not have to be. Okay, so here we have vertical asymptotes of rational functions, and this first comment, since a rational function is discontinuous only at the zeros of its denominator, that means that a vertical asymptote for a rational function can only occur at one of the denominator's zeros. Just as a reminder, a zero of the denominator could cause a whole or a vertical asymptote. So if you read that and you say it's very repetitive, the textbook fails to say that the zeros can cause a whole or a vertical asymptote, but we know that a vertical asymptote will only occur for an x value that creates a zero in the denominator. That is to say that just because an x value creates a zero in the denominator doesn't automatically mean that you have a vertical asymptote. There's the possibility it's a whole. So it's one of those nuanced details you have to focus on. So the following is a simple procedure for locating vertical asymptotes of a rational function, and we did this in our algebra review. Basically, you want to first make sure the fraction is reduced. So find the reduced form of a rational function, then solve for the zeros of the denominator. Another way that a textbook might communicate this is they say that vertical asymptotes exist at the zeros of an irreducible rational function. Let me fix that. Vertical asymptote exists at the denominator zeros of an irreducible rational function. Irreducible means that there won't be any canceling between the numerator and denominator. It's already in simplest form. So if it needs to be simplified, do that first, then find the zero of the denominator, and that will be a vertical asymptote. If the rational function has factors that cancel, it'll produce a zero that's a whole at those locations where the factors cancel. So let's look at this example. Is this irreducible? Well, the first thing we want to do is look at the factors of the numerator. We have a quadratic with a lead coefficient of 1, and we need two numbers that multiply to -2 but add up to +1. And then the denominator is difference of two squares, so it's x plus 1, x minus 1. So we see that this is going to cancel. X minus 1 equal to 0 gives us x equal to 1. This is a zero of the denominator, but it creates a whole. This is the irreducible rational function. So the denominator set equal to 0 gives us x equal -1, and this will be a vertical asymptote because it's the zero of a denominator of an irreducible rational function. We reduced it already, it is no longer reducible. So if we were to draw this graph, we know that at -1, we would have a vertical asymptote. And we know that at +1, we would have a whole. We take that +1 and plug it into the irreducible fraction to get the exact location of the whole. So 1 plus 2 is 3 in the numerator, and 1 plus 1 is 2 in the denominator. So 3/2 is where the location of the whole will be on the y part. So 1 is the x coordinate, 3/2 is the y coordinate. Right here is our whole, and we want to draw as an open circle. Now we can take a few other points, say what happens when I plug 0 into the irreducible rational function? We get 2/1. What happens when I plug in 2 into the irreducible rational function? We get 4/3, which is 1 1/3. And we can look at the irreducible rational function and say, what's the horizontal asymptote? We see that the degrees are equal with lead coefficients of 1. So the horizontal asymptote will be at 1. And now we have an idea of what the graph looks like. It goes through this hole. That's one branch. And just to be safe, we'll choose a number on the other side of the vertical asymptote. And when we plug it in, we get 0/-1, which is 0. So we know that these branches will control the path here. And we have our graph. So we have 2 points of interest here at -1. So what is the limit of this f of x as x approaches -1? And we would say dne. Why dne? Well, from the left-hand side of -1, we're going to negative infinity. From the right-hand side of -1, we're going to positive infinity. The left-hand side limit is not equal to the right-hand side limit, so we have dne. Now let's look at the limit as we approach 1. There's a hole there. The limit as x approaches 1 for f of x. Well, as we approach 1 from the left-hand side, we're getting closer and closer to 3/2. As we approach it from the right-hand side, we're getting closer and closer to 3/2. And we would say that this limit is 3/2. And now for clarity, if I said to evaluate f of 1, that means what point do we have there? What y value is at f of 1? That's where there's the hole. And we say this is undefined. So this is a good example for us to understand we have limits that equal negative and positive infinity, which are not equal. So we have a dne at the vertical asymptote. And we also had a hole in this function, which gave us a limit value, but we cannot evaluate the function there because there's no y value. The y value is a location of the hole, but is not a member of the graph. So limits at infinity means that as x goes to positive infinity or as x goes to negative infinity, do we get a value that we can say is finite? Let's go back. You can see in this graph, as it goes off to infinity, what y value is it getting closer and closer to? And we saw that this vertical asymptote is y equals 1. So that's the limit value as x goes to infinity. So we can say the limit as x approaches positive infinity for f of x equals 1. And that 1 is the horizontal asymptote. And if we were going to negative infinity, if we were going in this direction, we see the limit is the same because it is the same horizontal asymptote that the branch of the graph is approaching. So limits at infinity mean as x approach positive or negative infinity, and we have to put our focus on horizontal asymptotes if they exist. If they don't exist, then the graph goes either to positive or negative infinity, and we have to know the end behavior of the graph. If no horizontal asymptote, investigate the end behavior of the graph. So limits at infinity of polynomial functions. Remember in the first chapter, we spent time examining, well, what does the graph of x cubed do? Well, x cubed goes like this. So if I asked for the limit as x goes to negative infinity for x cubed, we would say, well, let's trace it. Negative infinity means I'm moving this way. What way is the y value moving? And we see the answer here is as x goes to negative infinity, so does y. Let's change this question. What is the limit of negative x cubed as x goes to negative infinity? Now we're talking about the lead coefficient of the graph. When the lead coefficient is negative, it flips the graph and it looks like this. And the same question is saying, what is the limit of negative x cubed as x goes to negative infinity? Well, as x goes to negative infinity, the y values are going to positive infinity now. So we want to review our rules for polynomial end behavior. If it were a odd degree graph, meaning x to the first, x to the fifth, x to the third, x to the seventh, we follow this x cubed example. If it were an even degree graph, let's say x to the fourth, then we would say, well, it's going to be similar to a quadratic. It's going to follow the reasoning of a parabola. And if I were to evaluate this, the limit as x goes to negative infinity for x to the fourth, we would say, well, as my x values go to negative infinity, my y values go to positive infinity. So review, polynomial end behavior. Limits at infinity and horizontal asymptotes. So we saw a little bit of this on the rational function. We drew the vertical and horizontal asymptotes, and that let us discuss limits to infinity. And this is the rules that we talked about when we graphed horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at 0. If the degree of the numerator is equal to the degree of the denominator, you take the lead coefficients of the highest degree terms, and that gives us the location of the horizontal asymptote. And if the numerator has a higher degree than the denominator, there is no horizontal asymptote. The limit is going to go to some form of infinity. We have to figure out if it's positive or negative. Find the horizontal asymptote of each function. So we're going to start by saying the highest exponent in the top is 4, the highest exponent in the bottom is 6. Since the bottom grows faster than the top, think about that. 1 over 10 is 0.1. If the bottom grows faster, 1 over 100 is equal to 0.01. 1 over 1,000, see how the bottom is growing faster than the top? We're getting closer and closer to 0. So this has a horizontal asymptote at 0. That means that the limit of f of x as x goes to infinity is equal to 0, because that's the horizontal asymptote. Now let's look at part B. We notice the top has a higher degree than the bottom. That means the horizontal asymptote does not exist, and the limit is either positive or negative infinity. Well, to evaluate that, we just have to do a little bit of analysis. And that analysis could be done by putting a positive 1 in if we're going to positive infinity, or a negative 1 in for x if we're going to negative infinity. So for part B, let's look at the limit as x goes to positive infinity of 2x to the 5th plus 1 over x cubed minus 7. And we know this is going to be some form of infinity. We just want to figure out what form. Now, we just need to consider the two highest degree terms and say, since x is going to positive infinity, let's plug positive 1 into 2x to the 5th over x cubed, because these two are going to determine the sign because they have the most influence. X to the 5th does far more than plus 1 in the expression, and x to the cube does far more than negative 7 in the expression. So when we plug in plus 1 into the lead terms, it gives us 2 times 1 to the 5th over 1 to the 3rd, which gives us a positive number. So we put a positive number there. If I go back to this and say, well, what if I wanted to see the limit as x goes to negative infinity for 2x to the 5th plus 1 over x cubed minus 7. Again, we know it's going to be some form of infinity because the horizontal asymptote doesn't exist. It's either plus or minus infinity. So since we're going to negative infinity, let's plug in negative 1 into the two lead terms. And we see that gives me 2 times negative 1 to the 5th over negative 1 to the 3rd, which a negative to an odd exponent is negative. So we have negative 2 over negative 1, which is positive 2. That means whether we're going to positive or negative infinity, this graph is going to positive infinity for the y values. So here is the rational function plugged in. If I hit graph, notice that if I go all the way to the left, it's going up to infinity. If I go all the way to the right, it's going up to infinity. This is what the rational function looks like for 2x to the fifth plus 1 over x cubed minus 7. The limit of the graph to negative infinity is positive infinity. The limit of the graph to positive infinity is also positive infinity. Just a quick summary, an infinite limit is a limit of the form where we're approaching a finite value for x and getting an infinite value for y. A limit at infinity is a limit of the form where we're going to an infinite limit for x, and we may get either a finite or an infinite limit for y. So that's the end of the lesson. Watch the video again, take notes, complete the practice, come to class with questions.